Sequential compactness. Some results related to sequential compactness. So first one is that a metric space is sequentially compact if it has a Bolzano-Weierstrass property. We know that if the metric space X3 has a Bolzano-Weierstrass property and X be any closed bounded subset of the real line, then the sequence Xn of points in X has a subsequence converges to a point of X. And this is also the definition of sequential compactness, because according to sequential compactness, every sequence Xn of points in X has a convergent subsequence. So in fact, sequential compactness is the result of this property. Now Lebesgue covering lemma. Let X3 be a compact metric space and Ui be an open cover of X. Then there is a delta greater than 0 such that if A is a subset of X with diameter A less than delta, then there is an I such that A is contained in Ui, means A is contained in some member of the open cover of X. Suppose this lemma is false. It means there exists a cover Ui which is open cover of a compact metric space X3, and for each n greater than equal to n, each n greater than or equal to 1, there is a set Sn of X with diameter less than 1 upon n, but this Sn is not contained in any member of the open cover of compact metric space. Suppose for each n belonging to n, we choose one point xn of this set Sn, which is a subset of compact metric space Xt. Since X is compact, there is a subsequence xnk, here k is in the suffix of n, of xn which converges to some point x belonging to X. But we know that Ui is an open cover of X, means Ui covers X. So there is one member of this cover Ui naught such that X belongs to Ui naught. But this Ui naught is open because this is a member of open cover. So we can choose epsilon greater than 0 so that open ball centered at X and radius epsilon is contained in this member of open cover. Let n greater than 1 be large enough for n greater than or equal to n such that 1 upon n is less than or equal to 1 upon epsilon upon 2, and distance of the subsequence x and k from X is less than epsilon by 2, because we know that the subsequence x and k converges to some point x belonging to X. So if y belongs to the set Sn, then distance of y from X is less than or equal to distance of y from x and k plus distance of x and k from X. This is by triangle inequality of metric space. But we know that diameter of Sn is less than 1 upon n, means diameter of Sn is at most 1 upon n. So this will be less than 1 upon n, and from here distance of x and k from X is less than epsilon by 2. But we have selected n so that 1 upon n is less than epsilon upon 2. So this is less than epsilon by 2 plus epsilon by 2, which is nothing but epsilon. It means Sn is a subset of a ball, open ball centered at X and radius epsilon, and we know that this open ball is a subset of some member ui naught of the open cover ui of compact metric space. But this is a contradiction, because we have assumed here that Sn is not contained in any ui for I belonging to I. So, but here we have proved Sn is contained in ui naught, which is a member of ui. Hence, open cover of compact metric space has a Lebesgue number. This number delta in this lemma is called the Lebesgue number of the covering ui, and if we select any number delta dash such that delta is less than or equal to delta dash, then delta dash also has this required property. We can also state this theorem as every open cover of sequentially compact metric space has a Lebesgue number. And we know that a metric space is compact if and only if it is sequentially compact. So proof of this theorem is same as the lemma which we discussed in earlier slide. Now next, a metric space has a finite intersection property for closed sets if every decreasing sequence of closed non-empty sets has a non-empty intersection. Now next result is a metric space is sequentially compact if and only if a collection A of closed subsets of X with finite intersection property has non-empty intersection. Suppose that Xt is a sequentially compact metric space. We know that in sequentially compact metric space, every convergent sequence has a convergent subsequence. Every sequence has a convergent subsequence. Let Fn be a decreasing sequence of closed non-empty subsets of X. Suppose Xn belongs to Fn, here n is in the suffix, for each n belonging to n. It means this Xn has a convergent subsequence Xnk with Xnk converging to X as k tends to infinity. Here k is in the suffix of n. This is by the definition of sequential compactness, because it is given that Xd is sequentially compact. Because this Xnk belongs to Fn for all nk greater than or equal to n and Fn is closed, it means this X belongs to Fn for every n belonging to n, because this set is closed, so it will contain its limit point. It means because X belongs to Fn for all n belonging to n, it means X belongs to intersection of Fn n equal to 1 to infinity, because X belongs in all Fn's. It means intersection of n equal to 1 to infinity Fn is non-empty, because we have found one element X belonging to this set. So it means if a metric space is sequentially compact, then a collection A of closed subsets of X with finite intersection property has non-empty intersection. Now the converse part, suppose X has finite intersection property. Suppose Xn be a sequence in X and we define Fn equal to Tn bar, means closure of Tn, where Tn is equal to is a set of sequences xk for k greater than n. Clearly Fn is a decreasing sequence of non-empty closed sets, so there exists X belonging to intersection of Fn n equal to 1 to infinity, because X has a finite intersection property. So we have an element X belonging to intersection of these Fn's. If we select a subsequence Xnk of Xn as follows, like for k equal to 1, there exists Xn1 belonging to T1. Here 1 is in the suffix of n, here k is in the suffix of n, such that distance of this xn1 from x is less than 1. Since x belongs to f1 and T1 is dense in f1, because we have defined fn equal to closure of Tn, means Tn bar. Similarly, because x belongs to fn1 and Tn1 is dense in fn1, there exists xn2 belonging to Tn1 with n2 greater than n1, such that distance of xn2 from x is less than half. If you continue defining like this, by induction, we have xnk belonging to fnk. If this is given to us, xnk belonging to fnk, we choose xnk plus 1 belonging to tnk, where nk plus 1 is greater than nk, such that distance of xnk plus 1 from x is less than 1 upon k plus 1. Then because it is given that because xnk tends to x, we see from this these steps that distance of xn1 from x is less than 1, distance of xn2 from x is less than 1 upon 2, distance of xnk from x is less than 1 upon k plus 1. So as k tends to infinity, then xnk will tend to x from here. So if xnk tends to x, as k tends to infinity, it means x is sequentially compact, because xnk is a subsequence of xn. So by definition of sequential compactness, because xnk converges to x, it means it is sequentially compact. X is sequentially compact. Now the definition of total boundedness. Let A be a subset of a metric space. We say that A is totally bounded if for every epsilon greater than 0, we can find a finite number of points xi where I lies between 1 and n, such that A is a subset of union of open balls centered at xi and radius epsilon. If this condition is satisfied, then we say that A is totally bounded. Now the characterization of compact metric space, although we have done proved all these in previous slides, but I have written here, for a metric space X3, the following are equivalent. Number 1, if X is compact, every open cover has a finite subcover. X is complete and totally bounded. Every infinite set has a cluster point or limit point. Every sequence has a convergent subsequence. Means it means sequential compactness. So this is the characterization of compact metric space, and all the 4 properties are equivalent to each other. Almost all of them we have proved in earlier slides. So thank you.